In this video, we're going to take a quick look at sufficient statistics, or the concept of sufficiency in general. And we will then follow up with a few results in a separate video. But first, let's take some definitions, what we mean by sufficiency. So, by way of background, what we want to do is we want to summarize the data that we collect in such a way that we do not lose any information, and we need to formalize this. So we're going to write up, first of all, what we mean. Now, if we have a sequence of random variables, then we can take a look at functions of these random variables. And of course, there are limits on what functions we want, because we need the result, the combination t of x, to be another random variable. If you're not sure what this means, you need to go back and see. This basically means that it's a measurable function. Now, so if t of x is a random variable, then we call this a statistic. So we're basically taking our random variables, taking our data and aggregating them in some manner or other. So we have, to be more formal, we would talk about t being the random variable, and it is some function of the initial collection. So capital T is little t of x. And we sometimes use this in a few different ways. We can use any of this as notation. Now, what we mean by sufficiency then is that somehow or other the distribution of the data conditional on t of x doesn't contain any information about the underlying parameter. So we have some probability density or mass function or just a CDF, and let's say here write it as f theta of x. So the function, the density is f theta for any theta in capital theta. Then we're going to define t as a sufficient statistic if the distribution conditional on t is a constant in theta. You might call this independent of theta, but we're using independence to mean something else in statistics. So you could also write this in a few different ways. You could use simply the conditional density, or you could say the probability of x in A given t takes a certain value is a constant in t. And here, this is pretty obvious intuitively that this is what we should have done, or what we mean. There's no information about theta left in the data once you condition on the parameter, on the statistic. We can then take a look at discrete parameters and show that if f theta is the joint PDF of x and q theta is the PDF of t of x, then we have sufficiency if this ratio is a constant in theta. That's one way of doing this. It's not the only way. But this requires us to find the density of t first, and then to check for sufficiency. And we can do this easily for some examples. For example, for a binomial of Bernoulli here, the sum of all the x's is a sufficient statistic, and that's fairly easy to see using this ratio. Similarly, x bar is sufficient for the location parameter in a normal, and so on. Now, there's an easier way to do this, where you don't have to first guess the sufficient statistic and then find its density. You can simply find it directly based on the functional form of the PDF of x. So if the PDF of x can be written as a product of two functions, where the first part only contains the x's through t in combination with the theta, and the second part, which contains any leftover x's, is only a function of x and not of theta. Then we've sort of taken the initial density, or probability mass function, and we ripped it into two parts. One part contains the theta and t of x, the other part contains only x's. Of course, if there was a theta separately, we would, without any x's, any t of x's, then we would just incorporate that part into g. This isn't too difficult to prove. You note that this is an if and only if sentence theorem, so we can do this either way. First of all, if t is sufficient, then you can define g in a certain way. Simply ask the marginal for t of x and define h of x as the conditional probability, and then we have the condition. So it's easy enough to go in this way. Now we need to go in the other direction. So suppose you have a g and you have an h, and then we simply say let q be the mass function of t of x, and then we evaluate the ratio between f theta and q theta, and we rewrite f theta in the way which is given according to the theorem, according to assumptions, and then we get to a result where we simply have to add up stuff, and in the end we find that anything involving theta actually cancels out, and the reason is that the g theta of t of x lies down here on the one hand, and then the marginal or the distribution, the mass function of t, is actually composed of a sum over all y's, where t of y is equal to t of the mass function of evaluate at the point y. And then again we get these g's, and the g comes out of the sum and cancels. So we've proven the theorem. And now we can use this in any number of ways. We can, for example, take the Gaussian, and what always happens in these various examples is if you take the density and then you expand the square and the exponent in this case, what you find is you have an x squared minus 2x mu plus mu squared. But if you insert a minus x bar and plus x bar, then you can expand these squares, and you find in the end that the cross product cancels, so you're left with just two squares. And now you note that the second square only contains x bar. The first square is sort of like s squared, the usual variance estimator, and we've now seen that the joint density is a function only of x bar and x squared. This is supposed to be a lowercase s squared. So that shows us that we can factor the density into something involving only x bar and s squared in this case, so that's a sufficient statistic. So h of x is just 1 in this case. And finally, we need a concept of a minimal sufficient statistic, because the entire dataset itself is a sufficient statistic, but you never actually want to use this. You want to use something smaller. You want to be summarizing the data if you possibly can. So a minimal sufficient statistic is a t such that if there is any other sufficient statistic, then t of x is smaller. In other words, t of x is a function of any other sufficient statistic. So we've completely reduced to get t. And these are sometimes unique, sometimes they're not, but we have a way of finding it. And the way of finding it is by taking two different data points, two different values, an x and a y, and looking at the ratio of f, the density evaluated at x and the density evaluated at y. If this ratio can be shown to be constant as a function of theta only when t of x is equal to t of y, then t of x is a minimal sufficient statistic. And the proof is here. as in the previous case, it sort of looks at these trajectories and is, apart from that, it's basically a thing you need to work out by hand. Now, it's an if and only if statement. Sorry, it's an if statement. The ratio has to be constant if and only if t of x equals to t of y. And again, what we do to use this theorem is we just look at these ratios and see under what conditions is t of x equal to t of y, and then we usually fairly easily find what is the minimal sufficient statistic. And you can do this for the Gaussian, for example. You take the ratio of two densities, and you, as you know, as we did before, you get this factoring, and now this is a constant in mu if and only if this number plus this number is a constant in mu, and of course that can only happen if x bar is equal to y bar. And the same thing happens to sigma squared, and these sigmas here cancel, but this term comes out to 0 in the exponent if and only if sx squared is equal to sy squared, so that the joint bivariate statistic x bar and s squared is minimally sufficient. So that's enough on sufficient statistics for now. We'll then move on and discuss ancillary statistics and take a look at completeness and look at some properties of complete sufficient statistics.